Yeah, right. All right, let me share my screen.
Must be the
And
magic smoke escaping.
yeah, that too. Um, all right. So yeah, so my main thing was my on-screen messages disappeared. The ones I use when I tag like different parts of the lecture, and my timer bar is off, but I've kind of got my timer bar working. But I got to watch here also, and and we're going 8-bit mode just for like retro purposes. So that's working.
Yeah.
Yeah. Now you know it's good stuff. All right, so we are up and running. All right, let's see. Did I miss anything in chat? Good attendance pings, excellent. Muting microphones, good. There it is. Always have a backup. Says yeah. Backups are done either once or 0 times. 0 if you've never lost your files. All right, cool. So we are at the end of week 8 here, which is awesome. We've got 3 weeks of school left, and that's it for fall quarter. And this class, we're going to miss 2 days for Thanksgiving. So coming to the end of the material, actually. So let's start with questions on the homework or on the PA or anything else.
Could you go through some of the questions on the homework? Because I think I have the rough idea down on how to do it, but I think being able to like say or like show like this means this is a bit lost.
So are we talking about the new homework or the homework that was just graded and handed back?
The one I was just graded, homework 6.
Okay, yeah, I definitely want to go through that. And so let's make some general comments on that, and then let's work through some specific problems. So general comments, induction proof. So most people are thinking about these things correctly. Most of the answers I saw, it looked like people were basically doing the right thing. Very few cases where people went backwards, where they assumed P of n plus 1 and then tried to argue to a truth. So let me just remind you, right, what we're doing with induction. We want to prove that some statement P of n is true, typically for all n, say, bigger than or equal to 1. Could be a different value. But the goal of the induction proof is to prove, some formula, some fact, something about tiling floors or throwing pies or who knows what, right? But we're always trying to prove something in the form of, a family of propositions, right? And so whatever you're asked to show, if you're asked to show that some inequality holds, you want to state a proposition, right, P of n, and then try to show that that is true for, a large number of cases, like all positive integers, for example. So we can play along with some specifics. So let's play around with. Yeah, go ahead.
In real life, in a real practicality, if you ever wanted to use this to prove something, you'd probably like see a pattern first, right? Like see something that's repeatedly true for lots of different things you try on it, and then you'd try to prove it.
Absolutely, that's exactly what happens. And you don't always necessarily actually do the proof on paper, but typically what happens is you're trying to write code, and let's say you're trying to come up with an algorithm to, I don't know, take some set of data and change it in some way to some other type of data. And you'll figure out how to do this by thinking about, here's a typical set of data I have in my head, and if I do these steps, yeah, okay, it turns it into the thing I want. That's great. And then you want to know, is this going to work like for other sets of data? And at some level, probably subconscious, you'll be thinking of it as a family of propositions. You'll be thinking, this works, in my test example where I had 5 pieces of data. if there was another piece of data, would it also work? And you'll say, oh yeah, it'll still work because all it does is change this, right? And since it worked for 5, it'll work for 6. And you'll also realize there's nothing magic about 5 and 6 about your base case, right? And from there you'll probably conclude, okay, this algorithm works for all these cases. Or you'll say, well, it only works if I have at least this many things, and so your base case would start higher, and you'd have to go in and put in some special code for other values. So we'll use this a lot, but not necessarily as explicitly as we're using it in this class. But yeah, it definitely pops up the way you described it. So let me play along with an example, which is we want to prove, and I'll pick question 5 from 3.4 to start because that's a good factorial question. Let's prove the sum from I equals 1 to n of I times I factorial is equal to n plus 1 factorial minus 1. So that's our starting problem. And it may be given to us in this mathematical form, or it may be given to us in a different form. It could come to us in the form of, prove 1 times 1 factorial plus 2 times 2 factorial plus n times n factorial equals the next factorial minus 1. But whichever way it's given to us, right, what we're trying to do is not prove that, 1 plus 2 plus 3 is equal to 4 factorial minus 1. We're trying to prove that this pattern is true for like all, numbers of terms that we would have. And so we create a proposition, right? So I'd say something like let P of n be the proposition sum from I equals 1 to n of I times I factorial equals n plus 1 factorial minus 1. Alright, so this is what I'm trying to prove, and this would probably be the next thing I would write on my proof sheet, right, is okay, I'm going to declare a family of propositions. So a lot of people started talking about P of 1 and P of n and P of n plus 1 and never bothered to say what P of n was. And it's clear to you because this is what you're trying to show, so P of n is going to be something like this. And it's probably clear to me because, we've been doing this in class. But to somebody on the street that you just hand this proof to, they're going to look at it and say, what is P of 1? What is P? What does that mean? Right? So you got to make sure you specify what this proposition P of n is. And then we can say, let's do mathematical induction. So how does mathematical induction work? We're trying to prove P of n for all n. So we do two things. First, we prove a base case, typically P of 1. And then we do what's called proving the inductive step. Prove that P of n gets us P of n plus 1, where n is bigger than or equal to 1. If we do both of those, then we will have proven this. This is what we're after, right? So I want to make sure that the person reading my proof understands this is what I'm trying to prove. Now what I'm really trying to prove is this. But I'm doing that by first stating a family of propositions, P of n, and then I'm going to say, let's prove P of n for all n bigger than or equal to 1. So if I have these three things on my proof sheet, this, and this, what's the experience of the person reading this? Oh, we're going to prove this fact about adding up, factorials. Okay, here's a family of propositions, which looks like this, and now the person says we're going to prove P of n for all n bigger than or equal to 1. What's that going to do? Well, it's going to prove if n equals 1, this is true. If n equals 2, this is true. If n equals 3, this is true. Oh, this is going to prove, this summation formula for all n bigger than or equal to 1. So this is equivalent to this. And if we can prove this, we're done. So we're going to do a bunch of steps, and at the end of it, we're going to state P of n is true for all n bigger than or equal to 1. That's what we're trying to show. That's when we get to say QED. Right? If the last statement of our proof is this, we're not done. The last thing we've proven is P of n implies P of n plus 1. Well, that does not tell us that P of n is true for any value other than 1. We have to tie these together with mathematical induction and say, therefore, P of n is true for all n bigger than or equal to 1. And then we get to say QED. So that was the main thing that I commented on people's submissions, was make sure that you don't skip any steps. Make sure that you define a family of propositions. Make sure you state that you're trying to prove that family for all n. Then go through the steps of proving the base case and proving this inductive step. And then when you're done, add one more statement saying, therefore by mathematical induction, this thing. And then you can say QED, and then you're done. All right, so let's actually do the work for this particular family of propositions. So the base case, is usually a simple demonstration. P of 1 states the following. It states that the sum from I equals 1 to 1 of I times I factorial equals 1 plus 1 factorial minus 1. All right. Well, this side is just, 1 times 1 factorial, which is 1. And this side is 2 factorial minus 1, which is 2 minus 1, which is 1. 1 does equal 1, so P of 1 is true. Now, if we wanted to be really formal, and I'm not asking you to be this formal, but I want you to believe that this is completely proper. So let me restate this. All right, so P of 1 says sum from I equals 1 to 1 of I times I factorial equals 1 plus 1 factorial minus 1. So I could do the following. I could say the sum from I equals 1 to 1 of I times I factorial equals 1 times 1 factorial equals 1 times 1 equals 1. And then I could say 1 plus 1 factorial minus 1 equals 2 factorial minus 1 equals 2 minus 1 equals 1. And at that point I could say, therefore, P of 1 is true. And anybody who understands, this language and understands factorials and summations would have to follow along and reach the same conclusion, because we have just shown that this left-hand side is equal to 1, and we've shown that this right-hand side is equal to 1, and P of 1 says that this is equal to that. Well, since they're both equal to 1, then in fact P of 1 is true, because this is the same as that. They're both equal to 1. But that's what's going on in proving the base case, right? We're not doing any funny substitutions. We're not assuming anything and then showing that something is true after that. We're just saying what P of 1 is very explicitly. It claims that this value is equal to that value, and we can calculate what this value is, because there's no variables in here, right, other than the summation variable, so we can calculate this sum and see that it's 1. And there's no i's or n's or anything over here. We can calculate this and see that that's 1. And, assuming we believe 1 is equal to 1, that tells us P of 1 is true. So then there's the inductive step, and so this begins kind of a sub-proof. So I might label this as, part 2, and here the goal is to prove P of n implies P of n plus 1. Okay, anytime that you want to prove something like if x, then y, what do? We start off with x, we argue, and eventually we come down to y. That's a direct proof. So we're always assuming this thing is true because that's what a conditional statement is. It's saying if this thing is true, then y is true. So we assume x is true and we see if we can show y is true. If we were doing an indirect proof, we would start off with x and we would say not y, and eventually we'd end up proving that false is true, and that's a contradiction. And so we'd conclude this was an error and therefore y must be true. We don't usually see indirect proofs in mathematical induction problems. So it's usually starting with x trying to get to y. So what's our hypothesis in this case? It's P of n. That's the hypothesis. Now we're going to say what P of n is, because, you know, if it's just P of n, there's nothing we can do with that. So I'm going to say sum from I equals 1 to n, I times I factorial equals n plus 1 factorial minus 1. It's kind of sad that I've got this memorized now. All right, we're trying to prove P of n plus 1. In other words, we're trying to prove that the sum from I equals 1 to n plus 1 of all of this stuff is equal to n plus 1 factorial minus 1. And so, you know, if you want to do an ignore, put it on the side. Don't put it as part of your proof. Right? If you say ignore and then you start putting things down here and you go on to the second page, are we still ignoring that, and so on? Put it off on the sidebar, right? And if you go back to when we talked about doing homeworks, I said, you know, you should work from top to bottom in a single column. That's part of why we're putting the ignore off on the side, right? You never want to write a proof that goes down here and then comes up here and continues and then comes down here and continues and then comes back and does something here and goes to the back of the page. You want to work top to bottom, single column. Okay? But this section over here, we're saying, hey, this is just where I'm thinking out loud. But we want to have it where we can look at it. So I'm going to make a note to myself. P of n plus 1 says sum from I equals 1 to n plus 1 of I times I factorial equals, and it's going to be n plus 1, so n plus 2 factorial minus 1. So that's what we want to show, and this is what we have so far. Well, this summation and that summation are pretty close to each other. So I'm going to write this slightly differently. I'm going to write this as the sum from I equals 1 to n of I times I factorial plus, and then I'm going to write in that last term for I equals n plus 1. And then I'm going to, you know, this is just a single summation of a single term just when I equals n plus 1. So this thing is equal to the sum from I equals 1 to n, I times I factorial, plus setting I equal to n plus 1 times n plus 1 factorial. All right, this is just a huge amount of dogmatic legwork we've done so far. We haven't really done anything except, you know, for adding an extra term here, but a lot of this has been sort of the formalism of you know, how we're setting this up and stating families and so on. So is everybody still with me here? Because this is where we get to that. Yeah? So this is where we get to that kind of like sparky section, that part where something happens. And we're going to do that by thinking about this and this, right? This is exactly the same as that. I know that this is equal to this expression because that's what P of n says. I'm trying to show that this plus this other thing is equal to that. All right? I'm not going to write that down, though. I'm not going to write that this is equal to that. If I do, my proof is no longer valid because I don't know that that's true. But what I can do is I can take this expression and I can use this and I can write the following. Sum from I equals 1 to n plus 1 of I times I factorial, that's this thing up here, is equal to this, plus this n plus first term. Right? This is just writing out what this summation means. But I can also say this is equal to, and now I'm going to, instead of this expression right here, the sum from 1 to n, I'm going to use this expression. I'm going to say this is equal to n plus 1 factorial minus 1 plus n plus 1 factorial. And that's the sort of pre-inspiration part, right? This is the kind of mechanical part, and typically, you know, the way we bridge from the preliminary stuff to the final stuff is something like this, right? It's mostly writing down what P of n is, looking at what P of n plus 1 says, and trying to use the statement of P of n somehow in the statement of P of n plus 1. So I guess that's the inspiration part here, is that by adding n plus 1 times n plus 1 factorial over here, right, we can change this summation into this summation. And so we get to this. And at that point, it's going to be sort of, you know, clever mechanical, mathematical gymnastics to show that this is actually the same thing as this. So now we've got a new subproblem. We're trying to turn this expression right here into n plus 2 factorial minus 1. And we can factor and we can distribute and we can replace, you know, n plus 1 times n factorial with n plus 1 factorial, different things like that. We've got a minus 1 right here. That's probably just going to be our minus 1 at the end. So I'm going to add another section over here, and I'm going to say, let's show n plus 1 factorial plus n plus 1 times n plus 1 factorial equals n plus 2 factorial. Oh no, is my video choppy?
Not so much to worry about.
Okay. I don't want to be a bad video game. Let's see, question 1. Others read this proof, so they typically ignore the ignore section. So the ignore section is really for you to figure out, you know, what it is you want to do to get you where you're going. But if you actually, you know, wrote this up as a formal proof, you probably wouldn't include an ignore section, right? You would have this and this and this. And, you know, this is this thing where when you read a proof, you don't need to necessarily know why the person went from one step to another. You don't need to know what their motivation or inspiration was for that. You just need to know that this step follows from that step, and that step follows from that step, and so on. But this is for my benefit and yours, right, to help sort of figure out, you know, where you're going to go and how you're going to get there. All right, so how do we show n plus 1 factorial plus n plus 1 times n plus 1 factorial is n plus 2 factorial? Doesn't sound like an obvious fact, but let's try multiplying. So let me do this on a different sheet with bigger. And this is still just, you know, for our own benefit. And once we've got this, then we'll go ahead and we'll show the critical steps to turn this into n plus 2 factorial minus 1. And then we'll be done. So we'll come back to this sheet in a minute. So one thing we can do is I don't have to do this, but if I don't, somebody's going to misinterpret this. So I'm going to keep writing propositions. We're going to say this is equal to, and I'm just going to multiply this out. n plus 1 factorial plus n times n plus 1 factorial plus 1 times n plus 1 factorial. And if I factor out the n plus 1 factorial, it's n plus 1 factorial times 1 plus n plus 1, which is n plus 1 factorial times n plus 2, which guess what? That's n plus 2 factorial. I did extra work. So we could have just factored out the n plus 1 and gotten 1 plus n plus 1. But we got there in the end anyway, right? So we can show that this is equal to that. So now we'll go back to our proof and we'll keep doing our algebra. And you want to do enough details so that whoever's reading your proof, that's me, knows that you didn't just sort of pull the answer out of thin air because it was what you were looking for, right? So I might pull out the n plus 1 factorial here and say, 1 plus n plus 1 times n plus 1 factorial minus 1. If you got time, you could rewrite this with the minus 1 at the end and stuff like that, but this gets us, n plus 2 times n plus 1 factorial minus 1 equals, and n plus 2 times n plus 1 factorial, that's n plus 2 factorial, right? Product of all integers up through n plus 1, and then you multiply by n plus 2, it's n plus 2 factorial minus 1. Alright, so now we've shown that this summation up to n plus 1 is equal to n plus 2 factorial minus 1. And so now we can say p of n plus 1. And the reason for that is definition of p of n plus 1. And what we just showed in proposition 3. And so therefore p of n implies p of n plus 1. Because we started with p of n and we proved p of n plus 1. And now we're going to say, therefore, p of n for all n bigger than or equal to 1. And the reason for that is mathematical induction. And that's what we were trying to show. So that's where we say QED. So this statement right here, that's what we were trying to show for this part of the proof, the inductive step. But the main thing we're trying to prove is p of n for all n bigger than or equal to 1. And that we get by taking this inductive step, combining it with the base case, and using mathematical induction, saying therefore p of n is true for all n. And that's our QED point. That's where we've proven what we tried to prove. So again, most problems that I looked at, the essential steps were there, right? And it was mostly a matter of making sure you state a family of propositions and that you state clearly what you're trying to prove in the beginning, show all of your work, keep the ignore section off on the side so it's not part of your proof, and when you're done, make sure you go back and you state that, this original thing you wanted to show is in fact true. And then you're good to go. What you don't want to do, so don't do this. And I saw this in a few cases. This is the only thing that is sort of a major backwardness to the proof. So, p of n, sum from I equals 1 to n, I times I factorial equals n plus 1 factorial minus 1. So try to avoid doing something like this, right? Like k equals n plus 1, sum from I equals 1 to k of I times I factorial equals k plus 1 factorial minus 1, right? This is an unproven proposition. Because this is saying the summation from 1 to n plus 1 satisfies this equality, and we do not know that. We only know that for some particular n that we have in mind, this statement is true. And we're trying to show that given that, this statement will be true for that given value of n plus 1. But I can't just write p of n plus 1, because we don't know if p of n plus 1 is true. And if you write p of n plus 1, and you spell out what that says, and then you subtract, both sides of p of n and so on and so forth, and you end up with 0 equals 0, you have not proven p of n plus 1. You've proven if this is true, then 0 equals 0. But you can't go backwards then and say, hey, since 0 equals 0, this thing 10 steps earlier must also be true. Right? That's the converse of what you're trying to show. So you're trying to show that this is true, and you can't do that by assuming it's true and showing that something else is true. Alright, so questions about that?
Probably gonna have one of those on the final, right?
Probably a good bet, yeah. Possibly two in different forms. Probably one. Alright, so are there particular questions from that homework set that you want to talk about the mechanics of? Because we had some inequality questions, we had some questions with fractions with big denominators and things like that. So were there any thing on those that you wanted to see?
I would have had a question about the factorials, but I finally figured it out.
Oh, cool. Awesome.
Sorry, we're pulling out the homework right now.
Okay. So there was the question about multiples of 3, and there was a couple of inequality questions. I think I gave you n factorial bigger than 2 to the n.
I want to say I had a hard time with the fraction, the 1 over 2i minus 1, 2i plus 1 equals n over 2n plus 1.
I was afraid someone was going to ask for that one, because that looks ugly.
That one was a little daunting.
So question 6.
It's 3.4 question 6.
So let P of n be the proposition sum from I equals 1 to n. So we're multiplying consecutive odd numbers and getting n over 2n plus 1. So let me do this with our ... notation so that we don't get too bogged down in symbols. So let P of n be the proposition. So if I is equal to 1, this is 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7 plus 1 over 2n minus 1 times 2n plus 1 equals n over 2n plus 1. That's a weird little statement there. So let's prove P of n for all n. This is bigger than or equal to 1. So P of 1, where n's equal to 1, basically it only has one term in the series, so it's just 1 over 1 times 3 should equal 1 over 2 times 1 plus 1. So this is a third, and this is a third. And so P of 1 is true. So let's prove P of n implies P of n plus 1. Alright, so first step we're going to do P of n, that's a hypothesis. Second step we're going to write that out, and I'm going to write it as, 1 over 1 times 3 plus 1 over 3 times 5 plus dot 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 plus 1 over 2n minus 1 times 2n plus 1 equals n over 2n plus 1. That's the definition of P of n. As with the other proofs, right, what we're probably going to do is we're going to write this out with one additional term added in. The term you get when you use n plus 1 instead of n. And we're going to try to show that that has the form n plus 1 over 2 times n plus 1 plus 1. And I think the challenge here is going to be just sort of working with the fractions and getting common denominators and so on. But let's just start with the algebra. So I'm going to write the exact same thing that I already had. And then I'm going to add one more term. So the next term of this series would be 1 over 2n plus 1 times 2n plus 3. And if you go back to the original summation, if I said I equal to n plus 1, this is 2 times n plus 1 minus 1. That's 2n plus 2 minus 1, that's 2n plus 1. And this is 2 times n plus 1 plus 1, that's 2n plus 2 plus 1, that's our 2n plus 3. And so we know this is equal to what that left part is equal to, plus the thing that we just added. And now we want to turn this into some form that looks like what we would have if we used n plus 1 instead of n. And so I'm thinking we just want to combine these with a common denominator. So I'm going to multiply this side by 2n plus 3 over 2n plus 3. Which is just multiplying by 1. So this is clearly equal to that because all I did was multiply this part of the expression by 1. But now I've got a common denominator on the bottom here. And so this will be n times 2n plus 3 plus 1 divided by 2n plus 1 times 2n plus 3. And then combine this out. Oh, that's weird. Do I really want a 2 there? Okay. 2n squared plus 3n plus 1 over 2n plus 1 times 2n plus 3. And then this looks like it's factorable. So this is 2n plus 1 times maybe not, times n plus 1. 2n squared and 2n is 3n 1 divided by 2n plus 1 times 2n plus 3. And then these things cancel. And so 2n plus 1 over 2n plus 3.
The 2n plus 1 cancels with 2n plus 1, so it's n plus 1 over 2n plus 3, right?
Thank you. Those cancel. So it's n plus 1 over 2n plus 3, which is n plus 1 over 2 times n plus 1 plus 1. Alright, so what does all of that show? it shows that this sum going up to n plus 1 let me just write it out and then we'll compare it. So this is all, you know, algebra. And so I'm going to rewrite this and say the sum from I equals 1 to n plus 1 of 1 over 2i minus 1 times 2i plus 1. That's what this left side is, right? This was the sum going up to n, then we added one more term for when I equals n plus 1. And this is equal to n plus 1 over 2 times n plus 1 plus 1. And that just follows from step 3. It's just a rewriting of step 3. But now if we go back and we look at what our proposition P of n says, right, what would P of n plus 1 say? It would say the sum from 1 to n plus 1 of this is equal to n plus 1 over 2 times n plus 1 plus 1. And so this is P of n plus 1. That's just looking at the definition of P of n plus 1. And then it's all the wrap up. Therefore, P of n implies P of n plus 1 for any n bigger than or equal to 1, and therefore P of n for all n bigger than or equal to 1 because of mathematical induction, and there's the end of the proof.
Please no fraction, or not this fraction, on the final.
I would have to grade it if I asked you to do it, and keep in mind I do have limits on how much I want to suffer while grading exams. So yeah, I probably would not give you a question like this, and there wouldn't be much point in it because, you know, more than half the effort on this problem is doing the algebra, and you know it's not an algebra course. If you really had to do this, you know, you would either sit down and do it, or you'd get, you know, Maple or some algebra software package to do it for you. I'm really after, you know, the concept of induction. So yeah, you probably wouldn't see something that horrifying on the exam, but you do in homework.
I found that one to be like significantly easier than some of the factorial ones.
Okay, cool.
Because I haven't encountered factorial problems before.
Ah, okay.
I definitely would agree, just because the factorial is a whole other animal.
Mm-hmm.
That one based the algebra, but
Yeah, and factorials take getting used to. If you haven't worked with them a lot before, then yeah, the intuition just isn't there. For a lot of people, fractions, especially with just a plain old 1 sitting on the top, can be equally unintuitive. And you know, when you're doing a problem like this, right, if you make one mistake, like, you know, canceling the wrong thing at the end, for example, there's really no mercy. The equations just will not work out, and you'll be left with, you know, some horrible improper fraction and no idea how to do it. If you get everything dialed in just right, then, you know, everything falls into place and cancels, and you get your beautiful answer out at the end. But it doesn't take much to kind of go astray. What would be a problem closest to what we might see on the exam? So I think this divisibility problem is cool. I think this is on par with what we've been doing. Question 1 in 3.4. Right, we did sums of integers, we did sums of squares, sums of cubes. It's more computation, but basically the same. This was one we did in class. That would be a reasonable problem. This one isn't too bad. It's still, you know, more complex than some, but I probably wouldn't go harder than something like this. But, you know, you may even see a problem we've already done. It's possible. This looks like an interesting one, but it looks like lots of minutia to get tangled up in with switching between the plus and minus signs. Let's look at that divisibility by 3 question. So I think it was trying to prove that that n times n plus 1 times n plus 2 is always divisible by 3. So, and I think we might have done this before. But let's make a family of propositions. 3 divides n times n plus 1 times n plus 2. Don't know if it's true, but that's what the proposition says. So P of 1 says 3 divides 1 times 2 times 3. Well, clearly 3 divides 1 times 2 times 3, because this is, 1 times 2 times 3. So, or we could multiply it out and get 6 and say, yeah, 3 divides 6, so that's true. So, second step, prove P of n gives us P of n plus 1. So start off with P of n, that's the hypothesis. This means 3 divides n times n plus 1 times n plus 2. Definition of P of n. Okay, what does divisibility mean? We have a definition for that. It means there exists some integer k such that n times n plus 1 times n plus 2 equals 3k. That's the definition of divisibility, or divides. Alright, so we want to prove something P of n plus 1. So let's just think about what that says. It says 3 divides n plus 1 times n plus 2 times n plus 3. Well, we already know something about part of this. We know 3 divides n plus 1 times n plus 2 times n. So let's think about what this is compared to what that is. And I'm not just going to multiply everything out. I'm going to try to be a little more tactical about this and say, hey, I know this thing is a multiple of 3. I want to show this thing is a multiple of 3. Well, I like this part of this expression. I know if I take this and I multiply by n, that's divisible by 3. So instead of multiplying everything out, I'm going to do the following. I'm going to say n plus 1 times n plus 2 times n plus 3 equals, and I'm going to distribute this. I'm going to say this is n plus 1 times n plus 2 times n plus n plus 1 times n plus 2 times 3. That's just algebra, right? I basically took this n plus 3 and I said it's equal to this times n plus this times 3. Well, now I'm in good shape because I know that this is a multiple of 3. That's from step 3. And this thing I can see is a multiple of 3 because there's a 3 right there. So I can continue writing, and I can say this first part, we already said that's equal to 3 times k. And the second part is 3 times n plus 1 times n plus 2. That's more algebra. And I can factor out the 3 and say this is 3 times k plus n plus 1 times n plus 2. That's more algebra. Well, I've written this expression as 3 times, an integer. And so I can say 3 divides n plus 1 times n plus 2 times n plus 3. That's definition of divides and what we showed in step 3. And this is what P of n plus 1 says. So P of n is true, therefore P of n implies P of n plus 1 for n bigger than or equal to 1. Therefore P of n itself is true for all n bigger than or equal to 1 by mathematical induction, and that's what we were trying to show. Kind of creeped out because I don't know what this thing is over here on this picture of a bookshelf, but it looks like Something scary.
I think that's a bee. Looks like a bee.
It looks like a bee. I
Yeah,
feel like
maybe
it's
like a
laying on
bee.
its side staring at me. That's kind of
Well,
weird.
that's
Yeah. Maybe we'll just go with that. All right. Cool. So yeah, we'll come back to induction in a little bit. And it will be there in the background of everything else we do, and like I say, it'll come up a lot in CSE222 in a different form. In 222, we're not going to be writing proofs. We're not going to be talking about families of propositions. We're going to be using this idea when we think about recursive algorithms, and that's going to be the key to doing a lot of what we do in winter quarter with various data structures like binary trees in particular. So this will, you know, come back in good ways down the road. All right, cool. Any questions on the counting stuff? Permutations, combinations, pigeonhole, all that stuff. All right, so let's go on. So let's talk about recurrence relations. I might be spelling recurrence wrong. I think it has an A. So a recurrence relation is a rule for defining each term of a series from previous terms. So we're just thinking of a series as, you know, an ordered collection of numbers: first number, second number, third number. I'm not going to get fancier than that, but just a sequence of numbers, right? For example, and a recurrence relation is a rule we can use to describe each number in some equation combining earlier terms in some way. So, for example, I could write a series of numbers like this. And let me think of this as, you know, term 0, term 1, term 2, term 3, term 4. Can you think of a rule for describing the nth term of this series as some function of the previous terms? Like, we know the next term will be 32, but how could I get that by using the previous terms in the series?
Would it be Sn plus 1 is equal to 2 times Sn?
Yeah. So Sn plus 1 is just twice Sn. And that describes this series of powers of 2 perfectly. So what is S5 going to be? It's twice S4. Oh, S4 is 16. Okay, S5 must be 32. What's S6 going to be? Well, if I know what S5 is, 32, it's just twice that. S6 is going to be 64. And so if we have a recurrence relation like this, we can use this to write out the terms of a series, provided we have one other piece of information. Now, if I tell you that I've got a series of numbers and they satisfy this rule, can you tell me what the terms of those series are? Can you tell me what S2 is? Or do you need some other piece of information? Somebody said it in chat. Say again? Yeah, you got to have a starting point. This is a true relationship, but if you don't know what S3 is, you got no way to figure out S4. Well, how do you know what S3 is? It's twice S2. But what is S2? I don't know. It's twice S1, but I don't know what S1 is. It's twice S0, but I don't know what S0 is. So we need an initial condition. So this is a recurrence relation. But we also need an initial condition. In this case, our initial condition was S0 is equal to 1. And now this statement of what Sn plus 1 is, this applies for cases where n is bigger than 1. Actually, it applies for bigger than or equal to 1. So if n is 1, I can use this to find S2. If n is 0, I can use this to find S1. But this doesn't apply for S0. Because this would say S0 is twice S minus 1, and there is no S minus 1. But for S0, we can use this initial condition. And so these two equations together completely define this series of integers. And so let's look at an application of this. Let's think about bacterial growth. So bacteria grows, according to some kind of exponential rule, because the more bacteria you have, the more bacteria you get. So let's think of an example. A bacterial population is initially 10. So you got 10, paramecium or whatever. I don't know if paramecium or bacteria. My bio teacher is like screaming right now. You got 10 bacteria, right? And suppose it doubles every hour. I don't know what happens in between the hour. This is a discrete structure, so we're just thinking about this, hour by hour. So at time 0, the population is 10. At time 1, where we think of 1 meaning, 1 hour, the population will be 20. At time 2, the population will be 40. And so we can define this with a recurrence relation, which says the population at time n plus 1 is equal to twice the population at time n. And the population at time 0 is equal to 10. And this is not a proposition, right? This is some sort of mathematical function. We tell it how many hours have passed, and P of n tells us what the population is at that time. So P of n is the population at time n. So we got to recalibrate our parsing algorithms. All right, so there's a recurrence relation and an initial condition, right? At time n plus 1, the population will be twice whatever it was at time n. And at time 0, our starting time, the population will be 10. And so again, we have an initial value and we have a recurrence relation. Now, are these looking familiar in any way? This pair of things where we have some initial value and we have some thing that applies to other cases? Right? You seen anything like that in the past week? Yes, thank you. Mathematical induction, right? This is the same structure of our setup for doing a proof by mathematical induction. We have a base case and we have an inductive step. Well, it's the same process happening here. And the parallel is, if I want to find what the population is after 5 hours, well, I can just say it's twice the population at 4 hours. and the population at 4 hours is twice the population at 3 hours. And the population at 3 hours is twice the population at 2 hours, and so on. If I keep doing this, eventually I will find out that, you know, this is 2 times 2 times 2 times 2 times the population at 1 hour, which is 2 to the 5th times the population at 0 hours. But at 0 hours, I don't have to use this recurrence relation. I know the population at 0 hours is 10. So this is 2 to the 5th times 10, so that's 320. If we don't have the initial condition, we just go down the rabbit hole forever. We never come back out. And if we don't have this recurrence relation, we know the initial population, P of 0, but we got no way of figuring out P of 1. So we got to have both of those things. And it's just like doing a proof by mathematical induction. If you want to prove proposition P of n is true when n equals 5, you start off with showing P of 0 is true, for example, with your base case. And then your inductive step says, well, since P of 0 is true, P of 1 is true. So you can work your way back up and get to P of 5. All right, now it turns out sometimes we can do what's called solving a recurrence relation. So, let me just tag that. So solving a recurrence relation means basically finding a formula, for example, for P of n. So P of n plus 1 equals 2 times P of n when n is bigger than or equal to 1, and P of 0 equals 10. All right. Well, so there's a few different ways to do this, right? One way is to start with P of 0 equals 10, P of 1 equals 2 times 10, P of 2 equals 2 P of 1, which is 2 times 10, which is 2 squared times 10. P of 3 equals 2 times P of 2, which is 2 times 2 squared times 10, which is 2 cubed times 10. And so we're seeing a pattern here, right? It's reasonable to believe that, you know, maybe P of 4, if we do the same thing, will be 2 to the 4th times 10. And so we could hypothesize that, you know, P of n is going to be 2 to the n times 10. And if you ask me explicitly, you know, what is P of 10, I can do this another 7 times. I can keep multiplying this by 2, and when I get to P of 10, I will find out that P of 10 equals 2 to the 10th times our initial population. But how would I prove that P of n is equal to 2 to the n times 10 for any n bigger than or equal to 1? How would I go about proving that? Somebody say it. You probably know it. Say it out loud. Mathematical induction, thank you. Right? So we can use mathematical induction to prove a solution to these recurrence relations sometimes. Because, you know, we would make a family of propositions that says, you know, P of n is 2 to the n times 10, and we'd show this is true for, say, P of 0 or P of 1. And then you have to show that if P of n is 2 to the n, P of n plus 1 is 2 to the n plus 1 times 10. And how do we do that? We use the recurrence relation. We say, well, P of n is 2 to the n times 10. P of n plus 1 will be 2 times 2 to the n plus 10. That's 2 to the n plus 1 times 10. That's P of n plus 1. I know I'm mixing my p's together there, but you get the idea, hopefully. So recurrence relations are really useful. And they're going to be super useful in computer science. A lot of the data structures we develop, as I said, in winter will be describable in terms of recurrence relations. And they pop up in lots of situations. So let's let's just end with bunnies. Which is weird because I had a dream about bunnies 2 nights ago, but they were actually cats. So I don't know if I was anticipating this lecture. Let's think about rabbit populations. Alright, so we're going to deal with idealized rabbits. So these rabbits have no predators. They live forever. The wabbits. They mate once they are 2 months old, and when a pair of rabbits mates, they have a pair of offspring. Okay, so it's a very idealized ecosystem. And so I want to start off with one pair of rabbits, and I'm just going to list, rabbits in pairs. They mate for life. So if I write the number 1, it means there's one pair of rabbits, right? Or you can think of these as tribbles that just, reproduce by eating if you like. But let's see what happens to our population over time. So at time 1, we have a single rabbit, or a pair of rabbits. And they are newborn, all right? So a month later, we have this same pair of rabbits, but now they're a month older. So this is like age, and this is time. All right, at time step 3, the following things happen. First of all, this rabbit pair becomes a month older, but also because they're now at least 2 months old, they reproduce, and they have an offspring. All right, at time T4, let me put in some vertical bars here. All right, at time T4, all the rabbits in the population get older. So this rabbit pair gets older, this rabbit pair gets older. And they're not ready to reproduce yet, but these rabbits are, now 4 months old, so they reproduce, so we get another rabbit introduced into the population. At time T5, all of these rabbits are a month older, but now we have 2 rabbits that are old enough to reproduce, and so we get 2 new rabbits in the population. So this is the 2-month line right here. All right, at time 6, all of these rabbits get older, and now we have 3 rabbits ready to reproduce, so we get 3 new rabbits in the population. And we'll go one more, time period 7, so all of these rabbits get older. And now we have 2, 3, 4, 5 rabbits ready to reproduce. So the population is growing. I'm very glad that people are up on their Warner Brothers literature, because that's fantastic. If you've never seen the opera version of this with Bugs Bunny, definitely do that. It's like the best film ever. All right, so the population is getting older, and it's increasing, but let's see what the population total count is at each of these time steps. So it starts off with 1. At time T3 we've got 2, and then the next time period we go up to 3, and then 2, 3, 4, 5, and then 3, 5, 6, 7, 8, and then at this next step 5, 8, 10, 11, 12, 13. So without actually moving the numbers around and putting in explicit quantities, let's think about what T8 is going to look like. Okay, the population at time 8 is going to come from 2 contributors. The first is all of these rabbits that are currently in the population. They're not going to die, they're still going to be there, right? So T8 is going to be equal to the population at the previous time step, because all of those rabbits are still in the population. And this population right here is not going to be old enough to reproduce, but this set of rabbits, right? over here. So this set of rabbits is not going to be old enough to reproduce, but this set is, right? So from 2 periods ago at time 6, we had some rabbits here. Those rabbits will be 1 month old in T7. Now they're going to be 2 months old. And certainly any rabbits that were old enough to reproduce at time 6 will still be old enough. And so in addition to, all the rabbits in the previous generation, all the rabbits that were present in time period 6 are now going to reproduce. And they're going to create new members of the population. So the population at time 8 is going to be the sum of the 2 previous population counts. And so from this kind of analysis, we can come up with a recurrence relation, which basically says Tn equals Tn minus 1 plus Tn minus 2. And that's maybe for n bigger than or equal to 3. And if n is 2, this doesn't make sense because we started with T1. So I'm going to put in a pair of base cases, which is T2 equals 1 and T1 equals 1. And so there's a recurrence relation that describes the population of rabbits at time n. And so this is the thing we mentioned briefly a few classes ago. This thing called the Fibonacci series. And Fibonacci series is characterized by this recurrence relation. Each term is the sum of the 2 previous terms. And the classic Fibonacci starts with just a pair of 1s. But if we started with some different numbers, we would get a different series. And it turns out there is a solution to the Fibonacci series. It's a little weird, and it might be off by 1 on the index, but let me just show you what this looks like, and we'll call it good at that. So it's 1 over the square root of 5 times 1 plus square root 5 over 2 raised to the n minus 1 over the square root of 5 times 1 minus square root of 5 over 2 raised to the n. And if you plug an integer n in, you get an integer out. And like I said, I might be off by 1 on the index, but if you plug in 8, you should get out 21, or maybe 13, but it'll give you the nth Fibonacci number. Not all recurrence relations have solutions. I don't think they do. But Fibonacci series does. And it's a weird one because it's got, these irrational numbers like square root 5, but this always turns out to be an integer, which is pretty cool. All right, so PA1 I graded and gave feedback back on, and PA1 looked great. No issues or worries about that. I'll post PA2 probably over the weekend, and we can talk about it on Monday. So my other plans for Monday are to talk about a few other applications of recurrence relations and look at how these tie into to some other things in computer science. We'll do some calculations with bit strings, and we'll basically see Fibonacci series popping up in multiple places. We'll also talk about a game called Towers of Hanoi, which will be a preview of winter quarter when we start talking about recursive functions. And we'll see how this game can be analyzed using recurrence relations, and we'll put together a little bit of code just as kind of an example of starting to play with some of this recurrence notion in software. And then we'll probably switch gears and talk about graph theory for the rest of the week. So we got Thanksgiving coming up one of these weeks. So, but anyway, that's my plan for Monday. I will let you out of here. Looks like you're about 3 minutes early. But if there's any other questions, go for it. Otherwise, have a fantastic week. Send me a ping on the way out, attendance ping in chat, and I will see you on Monday.
Thank you. Have a good weekend.
Thanks, you two.